This is lesson 7 called Products of Sum Design. You remember in lesson 6 we did a sum of products using min terms. In this one we're going to define what we call a max term. Now a max term is not a min term. That's easy to remember. Which means that the max term m0, big M0, is not min term little m0. So we can actually write big M0 is not little m0. But you remember what little m0 was. That was just not x and not y. So big M0 is just not that. And now we can use De Morgan's theorem to not the variables. So not x becomes not x, not y becomes not y. Change ands to ors and not the result. All these nots go away and we end up with x or y. So the max term big M0 is just x or y. Now we can do the same thing with the other ones. Big M1 is just not little m1. That is not min term m1, but min term m1 was not x and y. Again, applying De Morgan's theorem, we'll end up with x or not y. Big M2 is not little m2. Well, min term m2 was x and not y. Again, apply De Morgan's theorem, you get not x or y. And big M3 is not M3. Apply De Morgan's theorem to x and y, you get not x or not y. So, you remember how easy it was to remember the min terms. If there was a 0, you knotted it, and then you ANDed them together. So 0, 1 became not x and y. For max terms, everything is the opposite. If there's a 0, you don't knot it. If there's a 1, you do knot it. And instead of ANDing them, you OR them. So again, it's easy to remember. 0, 0 becomes x or y. This becomes x or not y. Not x or y. And 1, 1 would be not x or not y. So max terms are easy to remember. Now, how do we use them? Well, you remember when we designed our exclusive OR gate using the sum of products, we looked at the ones. For the product of sums, we look at the zeros. So here we have a 0, which means that z is not min term m0, because it's only min term m1 and min term m2. And it's not min term m3. So a 0 means that z is not min term m0, and it's not min term m3. So, by inspection, we can simply write what z is. Z is, look at the zeros, max term m0, means it's not min term m0. So it's big M0 and, remember we're ANDing these together now, and big M3. But big M0, of course, is just x or y. Big M3 is just not x or not y. AND them together, and we have a new equation for z, x or y, and not x or not y. So this is a different solution, but it also gives us the exclusive OR. We can draw a circuit diagram. Here, we're ANDing at the end. That is, this is a product of sums, so we have two OR gates rather than two AND gates that we had before, and we have the AND gate out here to give z. So we need to produce x or y, so we'll just connect this to x, connect this to y, and then here we need not x or not y, so we'll connect this to not x, connect this input to not y, and then the output z is just the AND of those. So this is a different circuit than we had for the sum of products, but they both produce the exclusive OR. You can see it from this truth table. If x goes 0, 0, 1, 1, not x goes 1, 1, 0, 0. Y goes 0, 1, 0, 1, not y goes 1, 0, 1, 1. X or y, or these together, it'll be 1 if either is 1. That is 1, 1, 1, 1, and a 0 here. Not x or not y. Well, we have 1s, 1s, 1, so it's going to be a 1, 1, 1, and here you have two zeros, so a 0. And if we AND these two columns together, we'll get a 0 here and a 0 here, and we'll get 1 here and 1 here, and sure enough, the output is our exclusive OR gate.